Good morning all. Today we are going to begin with the second module, that is DC motor drives. Earlier there were certain prediction that AC motor drives are going to replace the DC motor drives. But so far for variable speed control applications, DC motor drives are in dominance. This is because of their lower cost, reliability and simple control. DC drives are used in applications involving good speed control, better speed regulation and a good transient response. You are quite familiar with these terms. Speed regulation is actually defined as the change in speed from no load to full load speed expressed as a percentage of full load speed. Whereas transient response is actually the behavior of a drive during starting, braking and speed reversal condition. DC drives are mainly used in applications such as lifts, traction, cranes, hoists, etc. Even small power DC motors are in great use, such as for positioning control and tracking applications. You have already studied in detail about the various types of DC machines. Broadly, DC machines are classified into two. They are separately excited and self-excited. The self-excited DC motors are further classified into series motors, shunt motors and compound motors. These compound motors are further classified into cumulatively compound and differentially compound motors. You are quite familiar with this diagram, so they are just given for your reference. This is actually the diagram for a separately excited DC motor. So in this case the field winding will be excited separately. If you see in all the remaining cases, the field windings are excited by the same source which is being provided for the armature winding. So in the case of a shunt DC motor, the field winding is connected in parallel with the armature, whereas in the case of series motor, the field winding is connected in series with the armature. In the case of compound motor, this is actually a combination of both shunt as well as series motor. So here you will be able to see both the windings, that is shunt field winding as well as series field winding. In the case of cumulatively compound, the flux produced by both these windings are aiding in nature. Whereas in the case of differentially compound, the flux produced by both these windings will be opposite in nature. That is the difference between cumulatively compound and differentially compound DC motor. In order to analyze the performance of a DC motor, we will consider the steady state equivalent circuit of the armature. That is clearly shown here. This is actually the supply voltage. Here RA. In order to analyze the performance of a DC motor, the steady state equivalent circuit of the armature is taken into consideration. In this equivalent circuit, V is representing the supply voltage, RA is indicating the armature resistance, IA is actually the armature current and E is representing the back EMF. The voltage equation in the case of a DC motor is written as V is equal to E plus IARA, where E is actually the back EMF, IA is the armature current, RA is the armature resistance and V is the supply voltage which is being given to the DC motor. You have already derived the relation for armature torque or the torque developed in the armature in the case of a DC motor as T is equal to 0.159 phi ZIA into P by A. From there you can very clearly write that the torque developed in the armature is directly proportional to phi IA. So in the relation which I have mentioned, the term 0.159 is same as that of the 1 by 2 pi. Therefore the relation for armature torque can be written as 1 by 2 pi phi ZIA into P by A. Similarly, the relation for back EMF. The relation for back EMF is same as that of the relation for generated EMF in the case of a DC generator. That can be written as E is equal to phi P and Z by 60A. Now while converting this N, that is actually the speed in RPM to radians per second, you are quite familiar with that conversion, that is omega is equal to 2 pi N by 60. So while making suitable conversions here, we will be able to write that E is equal to Ke phi omega m, the constant which is appearing in the torque relation and in the back EMF relation will be one and the same. After this we will make the substitution of 3 in 1. Thereafter we will write the relation for omega m. See, after making the substitution of 3 in 1, we will be getting the relation 1 as V is equal to Ke phi omega m plus IARA, from which we will write the relation or we will deduce the relation for omega m which we can get it as omega m is equal to V minus Ia Ra divided by Ke phi. Further simplifying it, we can write the standard relation as V by Ke phi minus T by Ke square phi square into Ra. This equation is number. First we will consider the performance of shunt and separately excited DC motor. In this motors, as the field current remains to be a constant 1, therefore the flux which is produced by these two machines are also a constant. Already we know that from this standard relation, this K is actually a constant. In the case of shunt as well as separately excited DC motor, this flux also remains to be a constant 1. So we can write Ke phi as a constant, which is indicated as K. So from this relation T is equal to Ke phi Ia. Instead of this Ke phi, we can replace it by a term K. Hence this relation 2 gets modified into T is equal to K into Ia in the case of shunt as well as separately excited DC motor. Similarly, in the back EMF term, this Ke phi remains to be a constant, so this also can be written as a term K. Hence E can be written as E is equal to K into omega m. Thereafter, in this relation of omega m, instead of Ke phi, we will make the substitution of K. Hence the relation for speed gets modified into the form omega m is equal to V by K minus Ra by K square into T. In the case of a series motor, since the field winding is connected in series with the armature winding, the current which is flowing through the field winding is same as that of the armature current. Therefore, we will be able to write that phi, that is the flux which is produced in the case of a series motor, is directly proportional to that of the armature current. So in order to remove the proportionality, we will be multiplying it with a proportionality constant that is indicated here as Kf. So phi is equal to Kf into Ia in the case of a DC series motor. We very well know that from the standard relation, torque is equal to Ke phi into Ia. So in this relation, instead of phi, we will be making the substitution Kf into Ia. Hence the relation gets modified into form Ke Kf into Ia square. Making the substitution of phi is equal to Kf into Ia in equation number 4. Equation number 4 gets modified into this form. Not only just phi is equal to Kf into Ia substitution is made in equation number 4. In equation number 4, instead of the term T, we have also made the substitution Ke Kf into Ia square. So from the numerator and denominator, the Ia square terms and all gets cancelled, and finally we will be obtaining the modified form of equation 4 in the case of DC series motor in this particular form. So from this relation, it's very clear that omega m is equal to V by Ke Kf Ia minus Ra by Ke Kf. But for analysis purpose, we need the relation between, or the relation in terms of speed and torque. So in order to obtain the relation in terms of speed and torque, instead of this armature current Ia, we make the substitution from here. That is, Ia is equal to square root of T divided by Ke Kf. So after making the substitution of Ia is equal to square root of T divided by Ke Kf, we will be able to obtain the relation for speed as omega m is equal to V by square root of Ke Kf into 1 by square root of T minus Ra divided by Ke Kf. This is actually the relation between speed and torque in the case of a DC series motor. Whereas in the case of separately excited and shunt DC motors, the relation between omega m and T is this one. This both relation are used to analyze the performance of these motors. First, let's analyze the performance characteristics of separately and shunt excited DC generator. In their case, this is the relation connecting the speed and torque. Even if you are trying to increase the value of torque, there won't be much deflection in the case of speed. This is because the value of Ra is very, very small. So, how much ever you are trying to increase the value of torque, the change or the dominant change which is occurring in this particular term will be very small. Hence, there won't be a much significant change in the value of speed. So from this characteristics, you will be able to see very clearly in the case of separately excited. This is the same as that of the shunt motor. So even if you are trying to increase the value of torque, there won't be a much deviation in the case of speed. That means in both the cases of separately excited DC motor and shunt motor, the speed almost remains to be a constant one with the change in the torque. Similarly, we have mentioned in equation number 2 that torque is directly proportional to Ia. Sorry, torque is directly proportional to phi Ia, whereas in the case of separately excited and shunt DC motor, phi remains to be a constant one. Therefore, torque will be directly proportional to Ia. Hence, the characteristics between torque and Ia will be a straight line in the case of separately excited as well as shunt DC motor. Next, we are going to analyze the performance in the case of a series DC motor. In the case of series DC motor, the relation between speed and torque is this one. So from this relation, it's very clear that whenever you are trying to increase the value of torque, the value of speed goes on decreasing. That is very clearly visible here. Whenever we are trying to increase the value of torque, the value of speed is keep on decreasing. Similarly, the characteristics between torque and armature current can be drawn in the case of series DC motors like this. This is because in the case of DC series motor, torque is directly proportional to Ia square. In actual practice, you don't need to by heart these characteristics, you just need to know the relations in the case of DC series motor and in the case of DC shunt motor. Once if you are aware about these relations, you will be able to plot the characteristics between speed and torque by yourself. Similarly, if you are aware about the relation between torque, flux and armature current, that is torque is directly proportional to phi Ia. So in the case of a separately excited DC motor, the flux remains to be a constant one, not only in the case of separately excited DC motor but also in the case of shunt DC motor. As the flux remains to be a constant one, torque is directly proportional to the armature current. Therefore, the characteristics between torque and armature current in the case of separately as well as shunt DC motors will be a straight line, whereas in the case of DC series motor, as the flux is directly proportional to Ia and torque is directly proportional to phi Ia. So altogether we can write that torque is directly proportional to Ia square. So in that case, the relation between torque and Ia characteristics will be very much similar to that of a rectangular hyperbola. That you will be able to see it here very clearly. Next, we are going to see some numerical problems associated with the basic speed control logic which we have mentioned so far. First, we will see in the case of a DC shunt motor how we are going to solve a numerical problem. So here it's very clearly given that the ratings of the motor are 200 volt, 10.5 ampere and 2000 rpm. This is actually the rated voltage, rated current and the rated speed of the DC shunt motor, and it has an armature and a field resistance of 0.5 ohm and 400 ohm. It drives a load whose torque is constant. This is actually a very important point. Its torque is being a constant one at rated motor torque. And then you are asked to find the motor speed if the source voltage dropped to 175 volt. Actual speed of the motor is 2000 rpm, and this speed is obtained when we are provided this DC shunt motor with the rated voltage. Now you are asked to find the speed of the motor when you are reducing the voltage to, that is when you are reducing the supply voltage to 175 volt, keeping the load torque to be a constant one. So in this problem, actually the speed control is achieved, that is the change in speed is achieved by reducing the voltage which is provided to the DC motor, that is actually the DC shunt motor. So whenever such sort of problems are asked, first you draw the simple basic diagram of a motor, of the corresponding motor. Here it is actually the DC shunt motor. So the supply voltage which is being provided to this DC shunt motor is 200 volt and the supply current which is taken by this motor is 10.5 ampere. Now once when we are reducing the supply voltage to 175 volt, definitely the current which is flowing through the field current also gets changed. Since the current which is flowing through the field current is getting changed, so what happens is the flux which is produced in the machine when supplying with 175 volt will be different from that in the case of 200 volt. So first we will find the flux which we will be getting when we are supplying with 175 volt. For that, we will consider that the flux which is produced in the machine when we have provided this machine with 200 volt supply is phi1. Similarly, we will be able to obtain the flux produced at 175 volt supply is phi2, and its value in terms of phi1 will be 0.875 phi1. As the flux produced by this field winding is directly proportional to the field current, and the field current which is flowing through this field winding will be directly proportional to the voltage which is provided here. So from this we will be able to find that whenever we are provided with 175 volt, the flux which is produced in this machine is 87.5% as that of the 200 volt supply. It's clearly given that while giving 200 volt, that is in the rated condition or the rated load condition, the current which is taken by the motor is 10.5 ampere. Since the resistance of this field winding is very high, which is actually given here as 400 ohm, the current which is flowing through this field winding will be also very small. So we can assume that the whole current of 10.5 ampere is same as that of the current which is flowing through this armature. That is the current which is completely taken from the supply is flowing through the armature, with the assumption that the magnitude of field current is negligible. We are not taking this into consideration. Usually it is of very small value, so we are not taking into consideration here. So we can say that the current which is flowing through the armature is same as that of the current which is taken from the supply, that is 10.5 ampere when we are provided with the 200 volt. Next we are going to find the armature current when we are provided it with a supply voltage of 175 volt. In order to find that, a condition is given here is that the motor is running at load torque of a constant value 1. That is, even if you are reducing the supply voltage to 175 volt, the torque which is being supplied to the load is a constant 1. We are quite familiar with the standard relation, torque is directly proportional to phi Ia. Since the load torque remains to be a constant 1 in both the conditions, we can easily write that Ia1 into phi1 is equal to Ia2 into phi2. Ia1 and phi1 are the armature current and the flux when we are provided with the 200 volt supply, and Ia2 and phi2 are the armature current and flux when we are provided with 175 volt supply. So from this we can easily find the value of Ia2 as 11.4 ampere. So when we are provided this machine with the 200 volt, that is in the rated condition, the machine is taking 10.5 ampere current from the supply. While we have reduced the supply voltage to 175 volt, the machine is taking 11.4 ampere current from the supply. Now after calculating the value of Ia2 or the current which is being taken by the machine when we have reduced the voltage to 175 volt, next we have to find the speed. So in order to find the speed, we know the standard relation that speed is directly proportional to Eb by phi. So in the case of second case, or in case 2, when we are provided this machine with 175 volt, the corresponding back EMF Eb2 we have to determine, and the value of phi2 we are already aware about. Similarly, we have to determine the value of Eb1 when we are providing the supply with 200 volt, or sorry, when we are providing the machine with the 200 volt supply. So Eb1 can be found out from the standard voltage relation as V1 minus Ia1 Ra. All these terms values are already we are known about all these values. We have already determined some of them, and some of the values were given in the problem itself. In the same manner, we can find the value of Eb2 also. Once after knowing the values of Eb1 and Eb2, we can easily calculate the value of N2, that is the corresponding speed at 175 volt supply. And it is find out to be 1984.5 rpm. So from this, it's very clear that when we are provided this DC shunt motor with 200 volt, the speed was 2000 rpm. When we have reduced the voltage to 175 volt, the speed has been reduced to 1984.5 rpm. So we can very well say that this is one of the technique which can be used for speed control in the case of a DC drive. That is, by reducing the value of supply voltage, we will be easily able to achieve the reduction in the speed. Next, let's see a similar problem in the case of a DC series motor also. In this problem, the series motor rated voltage is 220 volt and its rated speed is 1000 rpm and its rated current is 100 ampere. The value of armature resistance and field resistance both are same and it is 0.05 ohm. You are asked to find the magnitude and direction of motor speed and armature current. Magnitude and direction of motor speed and armature current if the motor terminal voltage is reversed and the number of turns in the field winding is reduced to 80%, assuming linear magnetic circuit. See, in this problem you are doing two things. One is you are reversing the polarity of the supply which is provided to the DC motor. This is actually a DC series motor. In addition to that, you are also reducing the number of turns in the field winding to 80%. So initially this will be complete 100% field winding will be there under normal condition and the supply voltage will be given to the machine like this. Thereafter what we are doing is we are changing the polarity of the supply. That is, the positive sign will be coming here and negative sign will be coming here. So the armature current will be flowing like this. So definitely the back EMF polarity also gets reversed. In addition to that, we are reducing the number of turns in the field winding also. So in this case, after making the changes from the standard one, you are asked to find the magnitude and direction of motor speed and armature current. These are the two things which you have to find. That is magnitude and direction of motor speed, and similarly you have to find the magnitude and direction of the armature current. It's very clearly given that the motor is driving a load with a constant torque. It's very clearly given that the motor is driving a load with a constant torque. From the standard relation of the torque, we very well know that torque is directly proportional to phi Ia. In case 1, we can write T1 is directly proportional to phi Ia1. Since this is a DC series motor, the phi 1 value is directly proportional to Ia1. So we can write T1 is equal to K1 Ia1 square. Whereas in case 2, the MMF will be reduced by 80%. This is because the number of turns has been reduced by 80%. From the standard relation of the MMF, that is ampere turns, we very well know that MMF is actually N into I, even though the current which is flowing through this remains to be the same, but the number of turns has been reduced by 80%. Therefore, the flux produced also will get reduced by 80%. Hence, the relation for torque can be written as T2 is equal to K1 into 0.8 Ia2 square. It's very clearly given that the motor is supplying a constant torque load. That is, in that case, both the values of T1 and T2 will be one and the same. So, after making this equation, that is T1 is equal to T2, and making the suitable substitutions, we will be able to obtain the value of Ia2 as 111.8 ampere. That is the case when you have reduced the number of field winding turns into 80% as that with case 1. In order to maintain a constant torque, or in order to supply a constant torque load, the DC motor, this DC series motor, will be taking from the supply a current of 111.8 ampere. Now hereafter it's very clearly given that in the problem we have reversed the supply which is being provided to this DC series motor. That is the step 2 which we are doing. In step 1 we have reduced the number of turns to 80%, and in step 2 we have reversed the supply. So once after reversing the supply, the polarity becomes like this. Even the polarity for back EMF is indicated here. Before, the current which was flowing through this was 111.8. After reducing the number of field winding turns to 80%, that same current will be flowing in this case also, but only the direction of the current has been reversed. So in this case, the value of Ia2 can be written as minus 111.8 ampere. So we have find out the value of magnitude of armature current and its polarity after reversing the supply which is being provided to this DC motor, and then not only that, we have also reduced the number of field winding turns to 80%. So part of the problem is solved, that is the magnitude and direction of the armature current has been find out. Next we have to find the value and the direction of motor speed. For that we know the standard relation, speed is directly proportional to EB by phi. So in case 1 we can write N1 is directly proportional to EB1 divided by phi 1. Similarly in case 2 we can write N2 is directly proportional to EB2 divided by phi 2. In case 1 this phi 1 is directly proportional to IA1. So we can easily write N1 is directly proportional to EB1 by IA1. Whereas in case 2 N2 is directly proportional to EB2 divided by 0.8 into IA2. Hope it's clear for you. The current which is flowing in both these cases are different. In the first case the current which was flowing was 100 ampere, whereas in the second case supplying a constant torque load, the current we have determined was 111.8. But now we have reversed the polarity of the supply which is provided to this DC motor. So definitely the current flowing or the direction of the current has also been reversed. So the value of IA2 in this case will be minus 111.8. So after making the suitable substitutions in this relation, that is N2 by N1 is equal to EB2 divided by EB1 into IA1 divided by 0.8 into IA2. You must be very aware now that why this 0.8 comes here, and making the suitable substitutions we will be able to determine the value of speed as 1117.7 rpm. See, from this one another important concept can also be explained. What actually you would have expected was the speed to be a negative one, or the direction of speed or the direction of rotation of this motor might have been reversed, but here while calculating you are obtaining the speed as a positive value. That means in both case 1 and in case 2 the direction of rotation of the rotor remains to be the same one. That's why the speed is having the same polarity. Why it's happening even after changing the polarity of the supply which is provided to the DC series motor? Still the motor is running in the same direction as that of the case 1. Why such a phenomena is happening? See, the answer is very simple. If you wish to reverse the direction of rotation in the case of a DC motor, either the polarity of the field or the polarity of the armature winding has to be reversed. If you are reversing the polarities of both the field winding as well as that of the armature winding, then definitely the direction of rotation remains to be the same one. In the case of this series motor, you have reversed the polarity at the input side. While reversing the polarity at the input side, you are reversing the polarity which is being provided to both the armature winding as well as field winding. So definitely there won't occur any change in the direction of the speed or direction of the rotation of the motor. Hope it's clear for you. So in this problem we have clearly explained how the speed control in a DC series motor can be achieved by flux control method, because here we have changed the value of flux by reducing the number of field winding turns from 100% to 80%. In the previous problem, that is in this problem, we have seen that we can easily achieve the speed control of this DC shunt motor by reducing or by changing the supply voltage to a lower value. But in this case also that method of speed control can be done. But in this problem you are asked to find the speed control, or you are asked to find the speed corresponding to a change in the value of flux. So in this problem we have achieved the change in speed by achieving flux control. Hopefully the concepts explained are clear for you. If you have any doubt, you can either post it in the comment box or else you can ask through our WhatsApp group. Now all of you must solve the problem which we have explained now in your